This is a microscope. It is an optical instrument used to view tiny objects, such as a cell. Using a high-power objective allows a more detailed view of the sample, but it limits the area that can be seen. This trade-off between the magnification and field of view is a limitation of the microscope. The question now is, how can we increase the resolution of a microscope while maintaining a wide field of view? This leads us to my research topic, Fourier ptychography. Fourier ptychography is a computational imaging technique that hinges on Fourier transform and ptychography. In the context of imaging, the Fourier transform of an image is a sum of its complex oscillations. Ptychography is a computational imaging method that involves capturing diffraction patterns from a moving specimen's light and generating a high-resolution image of the sample. Back to Fourier ptychography, it employs an LED array that illuminates the sample from various angles. It does not involve movement of the slide, and intensity measurements are captured. To simulate this, a complex object is prepared. Each oblique illumination contributes an intensity measurement. Using the correlation between these oblique plane waves in the spatial and frequency domain, we can obtain a complex object solution that is coherent with all of the measurements. Experiments are conducted where accessible materials are used for practicality. This is a sneak peek of my results. I used the slanted edge method to get an estimate of the modulation transfer function. Comparing the MTF curves, an increase in spatial resolution is observed. In conclusion, Fourier ptychography successfully improved the resolution of a low numerical aperture microscope. If you are interested to know more, you can watch my thesis defense or contact me. I am Christene Necesario under the advisorships of Dr. Maricor Soriano and Dr. Ritz and Aguilar, and this is my thesis in a nutshell.